Let's talk about a word that, well, basically runs our modern world: algorithm. You hear it everywhere, right? It's behind your social media feed, the stock market, pretty much everything. But what is an algorithm really? Turns out the answer is way older and, frankly, a lot more interesting than you might think.
Okay, so if you've ever been stuck on a coding problem at 3 a.m., you might actually believe this one. This idea that algorithm comes from the Greek for number and pain, a painful number procedure. I mean, it just feels so right, doesn't it? But believe it or not, it's totally, completely wrong.
Yeah, the real story is so much cooler. It takes us all the way back to the golden age of science in the medieval world. So, to really get what algorithms are all about, we have to forget about painful numbers and meet the guy whose name accidentally became one of the most important words of our time. So, first things first, what are we even talking about here? An algorithm, it isn't some kind of digital magic, and it's not just for computers. At its heart, an algorithm is just a recipe, a set of instructions. And this right here is the key. Every single step has to be crystal clear, explicit, precise. There's zero room for guesswork. You could give these instructions to a robot or even a person who has absolutely no idea what the end goal is, and they could follow it perfectly. It's the ultimate instruction manual.
And here he is, the man himself. The word algorithm is really just a mangled Latin version of the name Al-Khwarizmi. He was a brilliant Persian scholar in Baghdad, a mathematician, an astronomer, a real genius. His book on calculation was so influential, in fact, we get the word algebra from its title, and he's the one who introduced the decimal system to the West. His methods were so famous that his name just became the word for the method itself. But here's the really wild part. The idea of an algorithm is way, way older than the word. Humans have been cooking up these step-by-step recipes for problem solving for thousands of years. Let's look at one that honestly feels like a magic trick. Seriously, think about it. Imagine you don't have multiplication tables memorized. Maybe you're a scribe in ancient Egypt. All you can do is add two numbers, double a number, and cut a number in half, and you just ignore the remainder. How on earth do you solve this? It sounds impossible, right? Well, there's a beautiful algorithm for it. All right, here's how you do it. You make two columns, an X and a Y. We're just going to keep having the number in the X column and doubling the number in the Y column all the way down. Now here's the secret sauce. Anytime the number in the X column is odd, you take its partner from the Y column and you add it to a running total. So we add 456, then 912. We skip the next one because 30 is even. Add 3648. You get the idea. Once X gets down to 1, you're done. And look at that. The total is 56,088, the exact answer. And this shows you exactly what we were talking about earlier. These are simple, unambiguous, mechanical steps. You don't even need to understand why it works, though it has to do with how numbers are represented in binary, which is pretty cool. You just have to follow the recipe. That is an algorithm. Okay, so we've seen an algorithm solve an ancient math problem, but they also deal with huge, messy, modern-day challenges. These aren't just for numbers. They're used to make decisions that affect the lives of millions of people. That's right. The U.S. Constitution says that the number of representatives each state gets is based on its population. But think about that. How do you fairly divide up a fixed number of seats, 435, among 50 states that are all different sizes? You can't give a state half a representative. You need a method that is fair, consistent, and repeatable. You need an algorithm. The recipe they use today is called the Huntington-Hill method. Basically, it starts by giving every state one seat. Then it uses a special formula to calculate a priority value for each state. Whichever state has the highest priority gets the next seat. Then you recalculate everything and do it again, and again, and again, until all 435 seats are handed out. It's a clear, precise process for a really complicated and deeply political problem. So we've seen algorithms as ancient math tricks and as modern political tools. But now we're going to get into one of the most powerful, elegant, and almost magical ideas in all of computer science. It's a way of thinking about problems called recursion. This is the secret right here. You take a big, nasty, hard problem, and you figure out how to restate it as a slightly smaller, slightly easier version of the exact same problem. I know, it sounds a little like cheating, but trust me, it's pure genius. To really get a feel for this, let's imagine we have some help. Let's call her the recursion fairy. Now, when you have a hard problem, your job isn't to solve the whole thing. Nope. Your job is just to do one tiny bit of work to make the problem a little simpler. Then you hand that simpler version off to the recursion fairy who, poof, magically solves it for you. All you have to do is handle that one simple step and know what to do for the absolute easiest case. Let's put the recursion fairy to work on a classic puzzle. This one is legendary. It was created back in the 1880s, and it came with this fantastic story, a story about the end of the world. So here's the setup. You've got 3 pegs, and on one of them is a stack of discs, each one smaller than the one below it. The goal is simple. Move the entire stack from the first peg to the last one, but there are rules. You can only move one disc at a time, and this is the important one. You can never, ever place a bigger disc on top of a smaller one. The legend says there's a temple with 64 of these golden discs, and when the monks finish moving the stack, the universe will end. With 64 discs, the task just seems astronomical. The number of moves is staggering. It feels completely overwhelming. Where would you even start? Well, this is a perfect job for the recursion fairy. So don't try to think about all 64 discs. That'll just break your brain. Instead, just think about the single biggest disc at the bottom. To move that one big disc to its final destination, what do we have to do first? Well, we have to get the other 63 discs out of the way, right? So, step 1, move the stock of 63 discs from the start peg to the middle spare peg. Step 2, now the path is clear, so we move that one big disc to the destination. And step 3, move the stack of 63 from the spare peg on top of it. And here's the magic. How do we move a stack of 63 discs? We don't. That's just a simpler version of our original problem, so we just hand it off to the recursion fairy. We've taken one giant, impossible problem and broken it down into 2 smaller, but still huge, problems, with one easy step in the middle. Our job is done. So if we follow that simple 3-step recursive algorithm, how many moves does it actually take to solve the puzzle with 64 discs? Well, get ready for this number. It's 2 to the power of 64 minus 1. Or 18 quintillion, 446 quadrillion. You know what? It's a lot. To put that number in perspective, if you moved one disk every single second, it would still take you over 585 billion years to finish. That's about 40 times the current age of the universe. So I think the world is safe for now. But the amazing thing is, we figured out how to solve this impossible puzzle with just 3 simple recursive steps. And that really brings us to the big idea here. From ancient multiplication to puzzles that take billions of years, algorithms are just recipes. And often the most powerful recipes are based on this one beautiful idea. Just find a way to make the problem a little bit simpler and then delegate the rest. It makes you wonder, right? What other impossible problems out there are just waiting for that kind of thinking? Thanks for listening.